Hello everybody, my name is Mr. Marshall and I will be your little video lecturer head in the corner of your screen guy for today. This class, it's applied physics on your schedule. Sometimes it's called PT for Principles of Technology. And this is the stuff that we are looking at. Ooh, there I am. We break it up into fluid, mechanical, electrical, thermal systems. The mechanical system is force, and we try to get a pretty clear definition of force because there can be a couple different ways we describe a force. So we want to have the same vocabulary when we do that. The next unit that we're going to deal with, so force is going to probably take us between 2 and 3 weeks, depending on how we break for labs. Pressure will be the next unit. We're going to look at fluid pressure as well as stuff like density, mostly just stuff with density and something called specific gravity you'll learn about. The next unit's electrical systems, where we look at voltage. A lot of electrical terms just get used incorrectly all the time. So we're going to start with voltage. Later we talk about amperage and power. We're going to start just by looking at what voltage is for an electrical system. And the thermal unit, we look at how heat gets moved around, how insulation works, stuff like that. So our force. The force is any push or pull on an object. So a satellite that's experiencing thrust, that's a push on an object. A handle on a wagon getting tugged, that's a pull on an object. What these things will do, pushing like in a garbage compactor can change the shape of an object, crushing. Changing the direction can be anything like a steering wheel, or just pushing on a basketball to send it flying through the air. Hitting a baseball when it's pitched at you should be a change in direction, that kind of thing. Things that speed up and slow down, like brakes or the gas pedal, those all apply a force. So in terms of whether or not a force is acting on an object, we're going to introduce the idea of net force soon. If a net force is acting, one of these things will be happening. So a force is when you push or pull on an object. We separate out mechanical force as being something that's in direct contact. Mechanical force has to have things touching, and usually things, forces get transferred through things like gears, where the gears, these cogs, are in physical contact with each other. They're turning each other. Belts, where a pulley on one side is turning a pulley on the other, connected with usually a rubber belt. Chains, like a bike chain, pulleys, cams that can turn linear force into rotational force, linkages, rods, sprockets, again, the list can go on. But these things have to be in direct contact. For the automotive guys, you should be pretty familiar with the idea that an automatic transmission is not a mechanical transfer of force. That's why you can sit there at a stoplight with your foot on the brakes. The wheels aren't moving, but the engine still does, because the wheels and the engine aren't directly in contact. Older manual transmissions, they are in direct contact, except when you separate them with a clutch. Mechanical force has to be in direct contact. Force transfers with a bike. You push on the pedal, you rotate a cog, the cog pushes on the chain pulls another cog on the wheel, transferred through the rod onto the bigger wheel, projecting the bike forward. So every once in a while we need to stop and see, when we're doing this kind of video lecture, if you're actually able to follow it. So this slide had pretty much one main idea, and what was it that I was trying to get you to learn? As this is the first time that I've tried it, and the first time I assume that you have too, but the idea of these videos is we can always rewind. We can go backwards and see, well, the main idea was probably underlined, and that's the idea mechanical force is transferred by direct contact. So that's the idea that I wanted you to take home. Again, direct contact, we're going to be dealing in depth with gears and transmissions, this idea of helically cut gears and the idea of straight cut gears, and how they change the speed. They're both turning, but the rate at which they turn is different when they're in contact. We'll also be looking at specifically how Mongoose plant makes their bike through various transfers of force, but bikes have a lot of examples of mechanical transfers of force. Now, as we talk about force, we do need to be specific about how we measure forces. The English system is what we use here, and it's used everywhere here. So force is measured in pounds. When you're talking about pressure, we talk about pounds per square inch. If you're talking about torques, you're talking about foot-pounds. If you measure the force of gravity, you're just talking about your weight in pounds. So English system, it's all pounds. The rest of the world uses newtons. They use newtons to measure force. So when you have some sort of a force being applied, they measure it in newtons instead of pounds. In this class, we're going to measure forces with a spring scale. The spring scales we're going to use in our first lab, and I'll show you. Another important piece is that the kilogram doesn't measure force. It measures mass. Mass meaning how much stuff you have. We'll cover this in more depth, but kilograms don't measure force. It's either newtons in the metric system or pounds in the English system. The metric system is sometimes called the SI system, or what you'd consider the international system. International system, or system international, metric system. So again, looking at whether you're keeping up. This video can be rewound, played back, whatever speed you want, but I was really hoping, but again, the stuff that's circled, underlined, that's what I'm trying to emphasize for you. English system pounds, metric system newtons, kilograms is mass. Really, that's all you need to take out of this. Now we get to mass. That's how much stuff you have in you. If you take an astronaut guy, send him up to the moon, he still has the same stuff in him. So a cheeseburger is still a cheeseburger, an astronaut's still an astronaut. When you send him up to the moon, he's practically weightless. That's different. That's not how much stuff he's got. That's how much gravity is pulling on him. Mass is, again, how much matter, and you can just think of it as stuff, doesn't matter. How much matter is contained in an object. Mass is the same everywhere. The kilogram masses that we have in this class is a kilogram mass anywhere in the universe. But a 5-pound weight is going to be weightless in outer space. The mass is going to be the same, but a 5-pound weight becomes weightless. We're going to be working on, pound mass is an English unit to measure mass. We never use pound masses. We usually just talk about pounds, but we can consider, say, a 5-pound object has a mass of 5-pound masses. So in outer space, it has a 5-pound mass. But really, for mass, even in America, we use kilograms. Conversions. The prefix kilo means 1,000. So if you have 1,000 grams, instead of saying 1,000, you can say kilo. So that 1,000, instead we just say kilo. 1,000 grams is a kilogram. 100 gram, that's basically 10 times less. We're moving the decimal point once over to the left. We do the same thing on this side. 100 grams is 0.1 kilograms. 10 grams, 0.01 grams. This is actually a very helpful table to copy down, because if you have 15 grams and you need to convert it to kilograms, you can use this pattern. If you have 320 grams and you need to turn it to kilograms, this is the pattern that you're going to follow in the labs to try to do that. So I'm going to give you an assignment next where you're going to work on converting some grams into kilograms. And the assignment is going to look, okay, maybe not quite yet. When we talk about weightless, again, astronauts are weightless, but they still have mass. Weight is called the force of gravity, and it's because masses attract each other. My mass is attracted to the Earth by gravity, so mass is related to weight when there's gravity. Weight is, again, pounds and newtons, because weight is the force of gravity. Weight is a force. We measure it with a spring scale. The scale in your bathroom has a spring in it. How much you compress that spring it determines your weight. Force of gravity is equal to your mass times gravity's pull. We'll be dealing more with this later. In the metric system, though, again, force is in newtons, and the way we figure out your pull in newtons is you take your mass in kilograms, you multiply it by 9.8. That's how you get newtons. So we measure force in newtons. Newtons comes from taking your mass and multiplying it by what our acceleration of gravity is. On Earth, it's 9.8. This is just a conversion that you're going to have to end up learning or using a lot. Sometimes in class, we're going to round that to 10 because it's a small margin of error. For quizzes and stuff, especially for lab work, I want you to use the correct number, which is 9.8. In the English system, we can convert mass into pounds just by multiplying by 2.2. Whoops, I don't know if you can see that very bottom there. Kilograms times 2.2 gives you pounds. All right. Okay, so I'm going to have you work out in the next bit of this presentation. There are going to be some questions where I want you to answer these. So you can go back into the slides. You can go back into the presentation. But if you're converting kilograms into newtons, well, there you go. Mass in kilograms times 9.8 gives you newtons. So that, hopefully you copied some of that important stuff down. All right, so these are going to be given to you in the next couple slides for you to answer. You can go back and use the video. There are slides online that you can look at those individual slides too. Okay, good luck.